Hello everyone. This week we did a lot, but the kind of core things was regarding input with mouse and collisions. So I'm going to review that today and hopefully get you a better understanding of what's happening. The first thing we'll go over is mouse events. So brief overview of what's happening. We kind of have called 6 events. We have a mouse enter, which will happen is that this rectangle or button will have a collider. And what we do is we detect between the collision between the mouse and anything that has a collider. And what happens is if collision happens, we get a couple events. If we are not in collision and then we go into collision, it'll be on mouse enter. So if the previous frame we're not, current frame we are, it will be on mouse enter, and you will see it. We have that on mouse enter is that top one. If our previous frame we are in collision with our mouse is in collision with a game object, and our current frame is also in collision, this will be on mouse over. This will be repeatedly called for infinite amount of time if the mouse just stays hovering over it. The next is if we are in collision the last frame, and then if we leave or if we're not in collision the current frame, there will be an on mouse exit or end. So you see how we're over, exit, we're over, exit. Now here's a couple of things that the next 3 are a little bit more complicated, and it would probably be good to actually look at a little bit of the code. So obviously, over, enter, it's kind of what I described. We loop through all the collisions this frame. If we're in collision, we call over. If we are in collision last frame, we call on mouse over. If we're not, then that means that we're in collision this frame, which means we call on mouse enter. And then if we are looping through last mouse collisions and we're not in collision in this frame, then that means that we exit. On mouse down is when we are, this is also makes sense. So if we are in collision and we press down, we see that we get a on mouse down. And that is that like top one right there that just showed up. And we are listening to in our inputs, because we already have mouse buttons down this frame, mouse buttons down, and mouse buttons up this frame. So it allows us to kind of do this stuff super easily. But if you are colliding down, or if your button is down this frame and you're colliding, then you call mouse button down. If you are down and you currently release the button and you're in collision, it's mouse button up. But if you are colliding down and up on the same game object or collider without missing out on collisions, then what happens is we call this mouse button up, or mouse up as a button. And it's like any button where you press up and down consecutively without removing collision. So I have mouse drag implemented, but let's see if I can mouse event. Let's temporarily remove mouse drag and show you. So if I'm there, I do down, up, it doesn't actually show it. So let's go that again. If I do mouse down and then go off of it and then release it, it doesn't. But if I'm down, up, it doesn't. So that's just kind of the quick idea of it. So the next thing to now consider is drag. If I am down and then the magnitude of the difference between my position of my mouse last frame and this frame is not 0, then I'm dragging. And those are the 6 mouse events that we covered. I think there's 6, but those are the mouse events that we covered. There is some stuff that we changed, like position last frame and mouse position delta, but a lot of the stuff is similar to keys down this frame and keys up this frame. The only major difference is inside of update. If we have a mouse position and a mouse position last frame, we calculate the delta by subtracting the two. And then if we have a mouse position, then we update the mouse position to be whatever the previous mouse position was, basically. So that kind of does it with inputs and how we have mouse events now. One really important thing is to think of them as events, because what's going to happen is that now you can call on mouse over whenever on any component if they have a collider. I will be showing you how to do that in my other video with my turn-based game, basically. But I'll elaborate on how on mouse over and what you can do with that type of stuff. But yeah, now let's go to collisions. The big thing with collisions we did this week is that instead of returning true if there is a collision, we're actually returning a value now. And that value kind of depends on what function we're calling in the process, but it all kind of correlates to the MTV, which in this case is the minimum translation vector, and that just means the smallest vector that will separate the two colliding shapes. So one way to test this is this. In here we have a mouse, and we're going to detect if that mouse is colliding with anything. Once it is colliding, we'll actually see a little arrow or a little line. What does this line do? Well, this line represents the MTV, which is the minimum translation vector. And what it's basically saying is that I'm currently in collision, and the best way, or the way to move in the direction that is the smallest is this red line here. So if I move that way, I am now out of collision. This is very useful in game programming because say I collide with a wall. I don't want to be partially stuck in the wall. I want to be able to be completely removed from the wall. Kind of a brief overview of what we had to do to change this. Instead of so first we have to check some things to return false now, but I'm going to primarily focus on truth, or whatever we would previously return true with. Basically, in our is overlap point vertices, we basically get the point and we subtract the min of the vertices, or the max of the vertices minus the point, and we get ever the smallest one is. This is basically returning the minimum distance from the point to either side of the interval of going left to right, basically. As we had in class, we had that line, and then we drew a point, or like a marker, and then we basically check which side is smaller. With is overlap vertices, we do the same thing, but instead of having a point, we have another list of vertices. So it's the math.max of A minus math.min of B, or the math.max of B minus the math.min of A. So now we have a range of two values, and we just have to see if there's any overlap within those ranges. Now is overlap point vertices direction. Now we're going in some sort of direction. And what we're returning in this is a vector pointing along the axis with a magnitude equal to the penetrating depth. So right here, we are along the axis of that vertex or to the closest line making up the shape, which is just that rightmost line. And we are just determining how far in depth are we relative to that line, or perpendicularly to that line. So we use the dot product between the point and the direction to get the projection of the point. And then for every vertex, we do the same thing. where we get the projection of the point into that direction. We then get the result, which is just the collision of over that point. And then basically, if we're not in collision, that means we return false. But if we are, that means that we need to return the direction of where we're going, normalize it, and then multiply it by whatever result we got, which is just how much overlap is happening. So we're getting the direction normalized times the overlap, or how much overlap we have. It's the same thing with vertices, but in this case, it is just two vertices rather than a point. But it is just a vector that's pointing along the axis with magnitude equal to its penetration, or how far it is inside the other game object. Now for is overlap. Now this is where we are actually starting to get the MTV, the minimum translation vector. And basically this is just the smallest vector that will push out that the polygon. So what we do is we go through we do a point and vertices. We get the shortest vector, which is the number at positive infinity, which is just the biggest. If there's anything smaller than this shortest vector, then we replace it. And this result is just the direction, or it is the vector that is pointing along the axis with magnitude equal to the penetration. So it's just the vector itself. And so the way you think about it is that every single edge or line of this polygon is trying to detect the collision between this point. And what we're doing in is overlap is we are just determining the shortest. Same thing with is overlap vertices, except with instead of a point, it is another polygon. Okay, and again, we just return the MTV. And now is collision and is collision game object. This is just a vector that is pointing us now out of the object. So as we showed in class, that sometimes we don't know the whether it is the direction of whether it is positive or negative. So what we do is we get the point and whatever point we're at, and we minus the transformed at position, and we get the dot product of the and whatever the result is. And then if the dot product is less than 0, we multiply by -1 because we are pointing in the opposite direction. Basically, we're checking between the center of the point and our current point. And then if it is in the same direction, or if it's in the opposite direction, we just multiply that result, which just is the magnitude in one direction, and we just multiply by -1, flipping it basically. And this is for both in collision point game object and in collision game object. And this is where then we finally actually get the MTV. I hope this kind of helped with this explanation regarding how we actually did mouse events and collisions, specifically the MTV. This was a lot, but hope you understand it now. Again, if you have any questions, comments, or concerns, please feel free to email me or talk to me or Rix before or after class.